Today I want to share with you a very powerful method for summing series, and the method goes by the name telescoping sum. It's called a telescoping sum. You can also call it a telescoping series. Now, why do we need this? There are sums you encounter in probability. Of course, you will also encounter them in other courses, but I'm only discussing probability here. Sums of this form, let's say sum of squares of integers, sum of cubes of integers. Sometimes you see sum of this form, products. So 1 times 2, 2 times 3, 3 times 4, and so on. And sometimes you can even have this. So 3 times 2 times 1, 4 times 3 times 2, and so on. To deal with these sums, you remember in your previous education, you might have heard names like mathematical induction and so on. The problem with those methods is that they are not straightforward. There is no way on earth you can remember those techniques. It's easy to forget. So the telescoping sum is a technique which is, if you understand this properly, it is very difficult to forget that. So let's clear the canvas and let me start with something which is very familiar to you. I take a sequence. So let's say S represents the sequence and Sk represents the kth term of that sequence. So if I subtract this kth term from the next term will be k plus 1. This is basically the difference. And it is called a forward difference because I subtract the present term from the next term. Another way of defining this difference will be to subtract from the current term the previous term, and that will then be a backward difference. But what we mean by delta in this video is the forward difference. The forward difference. So to see the usefulness of this difference, say I take this difference and I sum these differences for different values of k. Say I sum it for k up from 1 to n. So it will be delta S1 plus delta S2 and so on. So if I now plug these for each value of k, so if I plug this for k is equal to 1, what will I get? I will have to subtract the first term from the second term, because second will be the next. For k is equal to 2, I have to subtract the second term from the third term, so on. Maybe I should write the last two terms as well. The last will be, because Sn, so Sn has to be subtracted from the next. The next term is Sn plus 1. And this previous term will be S, and the previous term was Sn minus 1, and that will be subtracted from the next. So Sn becomes the next. Notice something very interesting here. This S2 cancel with this S2 because of the plus and the minus. This S3 must cancel with something there because this S3 will appear with a minus sign. Similarly, this Sn cancels with that Sn, So the two terms which remain uncancelled is this S1, because there is nothing, because there is no term before that, and there is no term after that, so this one remains intact. All the other terms, and remember, this Sn minus 1 is a minus, has a minus sign. It will have a plus sign somewhere there, so that will also cancel out. Let me use a red pen for that. Now you will see why I use the term telescoping, because when you go from one term to the next, each time part of that term will cancel out a part of the next term, and part of that will cancel out a part of the next term, and so on. So it looks like you are unfolding a telescope. If you have seen how a telescope is unfolded, you will understand the name of this method. So it turns out that the sum of these forward differences from 1 up to n is Sn plus 1 minus S1. And if you understood the mechanism here, this n plus 1 is that n plus 1 basically. So if I change that n to something else, this will also change. If I change that, for example, to n minus 1, then this will become n, because the next term from n minus 1 will be n. Similarly, this one and this one have to match. So if I change this one to 2, then this will also become 2. If I change that one to, for example, minus 1, this will also become minus 1. So I hope you are following me. Now we need to take an example. Let's take a simple example which you already know the answer to that. So this will just get us going. Say I have a fixed ratio and I take powers. So this will give me a geometric series if I try to sum this. So remember, R is a constant here, and the sum, the sequence depends on K. So for each value of K, you will have a different power of R. So we want to see the form of these differences, delta Sk. So it will be subtract the kth power from the next power, K plus 1. You can take that R to kth common, because it is there as well as there, and here you get R minus 1. So the difference depends on R and K, and only K is going to change. R will remain constant. So say I come across this summation from K1 equal 1 to K equal n, and I come across this summation. Of course, the geometric series, you know the answer, but let us see. I don't know if you remember how you got the answer. Don't tell me that you remember the formula, because remembering something doesn't add to any understanding. So you should notice one thing here. Sorry. This power of R and this power of R. So I was actually setting the stage for that. This R minus 1 is the only problem. So I can either take that R minus 1 to the other side, or I can start with this series. So if I divide this series by R minus 1, definitely then I also have to multiply this. I have to multiply as well. And that now I have that same r minus 1 times r to k, r minus 1 times r to k. I can now replace this with that, because that they have to match. Yeah, they have to match. So I'm not doing anything mysterious here. So I have, sorry, I have achieved so far that r minus 1 is not going anywhere, that r minus 1, and I have been successful in writing that original sum is a telescoping sum, a sum of finite differences. And I know the answer to that. The answer to that is of the same form. Yeah? So it will be Sn plus 1 minus Sn, and that r minus 1 is in the denominator. Now tell me, what will be this Sn plus 1? I know the formula. The kth term is r to kth. So Sn plus 1 will be r raised to n plus 1. And let me change this a little bit, because maybe a more standard sum will start with 0. So let me change this. It will not change the method, but it will just make it similar to what you have been doing. Yeah. So this will then be 0. Yeah? Because the first term, the first value of k is 0. So instead of S1, it will be S0. So that will be S0, S0, so R to 0th, R to 0th. And R to 0th, you know, is 1. I hope you agree that this is exactly how the sum should be. You can compare it with your previous knowledge. Now we will attack some more complicated problems, just to see that this method was not introduced just for this geometric series. So let me clear the canvas with the hope that you will remember the standard formula, and say I this time take another example of this sequence, and that example is k times k minus 1. Yeah. So take the difference. It will be k times k minus 1, the present one term, and the next term will be this k will become k plus 1, and k minus 1 will become k, the next term. K is common, so here I will have k plus 1, and here I will have minus k. You have to be careful, and plus 1, yeah, because this minus and this minus will become plus, and k cancels with k. This plus k and this minus k cancel out, and you are left with 2k, 2 times k. Now this should give us a hint that we can attack summations of this form. If I need a sum of integers from 1 to n, again you will know the answer, but This is the second example, and this will lead to the next example, and that example will be complicated. So this k and this k, this 2 is needed to make a match. So I divide this series by 2 and I multiply this by 2, and when I multiply this by 2 and divide this by 2, this 2k will match this 2k, which means that I can again write this series as a telescoping series, because that 2k equals that difference. Yeah, we have brought it to our strength. Now I know this denominator will become 2 because of that half, and I know that it will be, let me just repeat that, it will be Sn plus 1, yeah, because that one is n, and the first one will be S1. Yeah. So S cap is this one, so just plug n plus 1 there, so k will become n plus 1 and k minus 1 will become n, for k is equal to n plus 1, plus 1 minus 1 cancel out, and for 1 setting k equal to 1 will 1 minus 1 will cancel out, so you have minus 0, and you can see that that is exactly the answer you were expecting. So after you gained some confidence, we can now attack the next example, and that will justify the use of this method, because that is something very complicated. So I am taking, sorry, use black ink. I am taking, for my sequence, this time I go for something more complicated, and I start with k, then k minus 1, and then k minus 2. So work out the difference. Yeah. So here I will have the original a k, k minus 1, k minus 2, and here just work it out. First k will become k plus 1 because I am going for the next term. This k minus 1 will become k, and this k minus 2 will become k minus 1. Now notice something very interesting. This k times k minus 1 and this k times k minus 1 can be taken common. So if I take that common, k times k minus 1, you can, remember this minus sign, so this k will cancel out with this k because that is plus and this k will be minus, and this minus and this minus will be plus, so this 2 has to be added to that 1, so I will get 3. Yeah. Now this suggests that I can attack sums of this form, k times k minus 1. K goes from, this time I go from 2 to n, because if I set k equal to 2 equal to 1, that 1 minus 1 will cancel out and I will start with a 0, so there is no point writing that. So I again divide by 3 and multiply by 3 because I need that 3 there. K equals to n, and I will have 3 here. 3 times k minus 1. So I have matched this term with that term. So essentially I succeeded in writing that horribly complicated series into a very simple telescoping series, because this 3 times k minus 1 is that same delta. So I am preparing the problem to my strength. I know it will work. So 1 times 3 and 1 divided by 3, and here I will have s n plus 1, if you remember the formula, and this will be s2 because this started with 2. Yeah, so if this is 2, this has to be 2. And I can now plug in. So take 3 in the denominator. Sn plus 1. I know the formula, this one. All I need is to plug n plus 1 for k. So it will be n plus 1 for the k, then the next one will be n, and the next one will be n minus 1. I'm just plugging n is equal to 1 for k. And if I plug k is equal to 2, that 2, when it comes here, 2 minus 2 0, so it will be 0. So I don't need to do anything else. And I have my answer. This n plus 1 times n minus 1 can be written as n squared minus 1 and times n, and you have a nice expression. Now this, once you have this sum of these following factorials, you can attack another sum which may not be possible to work out directly. Let's say you want to have a sum from 1 to n of squares of natural. Let me write that k times k minus 1 because I want that form. I'm not changing anything in the summation. Now this will give me k squared minus k. K times k is k squared minus k. So I have introduced minus k from my side. There I only needed k squared. So I can now compensate for that, and I will have the summation from 1 to n k. So you see, this plus k and this minus k cancel out, and I am left with the original sum. Now I don't need to do anything else because I know how to deal with this. I know the formula, that one. And I also know how to deal with this. Yeah? So if I write this expression, for the first one I will have n squared minus 1 times n over 3. And for the second, you already know the answer. It is n plus 1 times n divided by 2. You simplify this and you should get your answer. So that was it. You can, as an exercise, because I don't need to tell you everything, you can try a general form of that. Yeah. So before that, if I express, if I recognize some pattern that I have 3 factors starting from k. So this is called a falling factorial. You start from k, you go down, and you stop when you have 3 factors. So I start from k, 1 factor, then 2 factors, and then 3 factors. I write that 3 here. So the number of factors will be here. If I now, instead of this, if I go with this example, that I start from k and I use a falling factorial of order m. So k, k minus 1, k minus 2, and I'll stop when I have m factors. This telescoping method will deal with that as well. That is something I leave for you, and that is yeah, the end of this video from my side. Give me feedback on this mode of teaching.